I think we are still waiting for some students, so we'll begin in 2 minutes. Okay, let's begin. So last time we talked about the physical layer, and also today's lab you will start to looking at the circuit programming. Okay? And the TAs will be there, go through the requirement. I think there are 5 steps that you need to finish on the client program. Okay, and you need to demo to the TA in the next three labs. Okay, and you have 2 weeks, I think. If you count the lab, actually there are more than 2 weeks, right? 2.5 weeks, close to 3 weeks to finish it. Okay. Okay, let's begin. So we were talking about the physical layer after we talked about circuit programming. Okay, and we mentioned there problem with the physical layer is really the signal, right? Each signal, the voltage, for example, each signal represents a bit, right? Whether it's 0 or 1, okay? And we can sample these bits, right? But there's there's an issue here, right? So because the clock may be different, okay, in different system, and when you send, there may be a shift of the clock. So how can we identify like or avoid sending long stream of zeros or ones that can, for example, be the same, low signal or high signal, right? So then we probably will miss some of the 0 or ones, right? How can we avoid that? That's the focus of this lecture. Okay. Uh, I see a student ask, can it be finished during the lab period? Yes, we have 3 labs, right? So for the circuit programming, the answer is yes. You can just work in the labs period if you think you are confident, right? But the first one will be mainly teaching you guys how to, what's the task and how to work on them, right? So the second and third lab is for you to work on and demo. But it's the safest way, of course, if you have time, you can work on, offline, and then when you're ready, you go to the lab, right? Then you can ask TA what questions you have, and do a demo by the third lab. Okay. Okay, so let's recap what we had last time. So here we know that each system itself, let's say each host, have a clock. Okay. And but a naive way is called a non-return to 0, right? If your clock is perfect, of course you can just do this method, right? 0 is a low signal and the 1 is high signal. Okay, but the problem is that when your clock is shifted a little bit, right? Like in this slide, we see that if your clock is slightly shifted, like here, then you are in trouble, right? Because originally maybe the sender thinks there are 8 1 bits, right? Because of the long string of ones, then and the clock shift, then you think that the receiver thinks there's only 7 clocks passed, and only 7 ones instead of 8 ones. Okay, and to avoid that, you need something like, for example, let's assume we have this long stream of ones, right? So we have a NRZ I, right? I is inverted, which means whenever I see 1, I invert the signal. Okay, 0 means keeps the signal. Okay, in that case, if you have a stream of ones, it will always be low, high, high, low, low, high, right? So you can easily detect there's this kind of inversion. Okay, and you will not miss any ones. Okay, but the problem is that you can also have a stream of long zeros, right? So how do we address this problem? So the solution is, instead of using original bits, okay, like you can have many zeros. Okay, for example, if you can have 2 such 4 bits, which are all zeros, right? Then you're in trouble. You have 8 zeros, which is a long stream. And we want to avoid that. The solution is that you can re-encode. You have a lookup table. Whenever you see these 4 bits in the original data bit stream, then you kind of you append these 5 bits into the sending bit stream, right? And when the receiver sees this bit stream, it will look up and replace with original bits, right? So why this kind of solution will solve the 0 problem, right? The long stream 0, because we can encode it in a smart way that, there's only 1 0 from the top, right? You will not see anything with the 0 0 or something else. Okay, only the 0 and most 1 0 at the beginning, at the head. Okay, as a tail, you will see at most 2 zeros. Okay, and actually this scheme minimizes such you can 2 zeros and 1 0 as a head. Okay, so even in the worst case, right? In the worst case, you will see 3 zeros. Okay, right? So for example, this is a previous 4 bits, right, encoded as this one, and the next 4 bits, unfortunately, you have another one that had it with 0, right? But then in that case, there are only 3 zeros. Okay, 0 0 0. Then immediately see 1. Okay, and if you see 1, then because this is the NRZI, right, it will be flipped. Okay, so you will at most have 3 zeros, which means your signal will hold just over 3 clocks. Okay, and 3 and 2 are still, easier to differentiate, right? 3 and 2, right? For example, you have this, and this 3 and 2 is still quite a big difference. Okay, but if you make it really 10 and 9, the difference really small. Okay, then that's in trouble. The receiver cannot fix it accurately. Okay, and the problem that we have a trade-off of 80%, right? The signal will be instead of sending 4 bits, we will send 5 bits, right? So which means 1 bit space is actually wasted just to address the consecutive 0 problem. Okay, and then we can encode these 5 bits using NRZI because we don't have long zeros. Okay, we can have long ones, right? So but inversion of the 1 bit will solve this. Okay, as long as we also don't have the long zeros, it's solved. Okay, and so lastly, we stopped on this slide, right? This is actually the last slide. Okay, so there's another encoding method called Manchester code, right? So what is this method? Basically, this is even more straightforward, right? So we told you that if you flip, right, immediately the computer can detect it. Right? So why not just a flip, right? For example, if I have a 0, I flip from low to high, okay? Well, I have another 0, low to high, because this bit ends with high, right? Because 0, low to high, okay? And but this also 0 start with low, so there's also another flip here, right? So this is automated by this, okay? But this here, the flip is really the flip in the middle of the clock, okay, right? So for example, we have 1, this is high to low, okay, high to low, and 0, low to high. So in that case, you can see that, hey, we will not miss any bit, right? So because there's no long holding of the same level, right, low, high, okay? Each clock will have at least 1 flip, right? So you can see in this clock, we have 1 flip, in this clock, we have 1 flip. And if you have this happen, actually 1 clock, you can have 2 flips, okay? You can detect those flips, right? And so that addresses the problem. What's the weakness? The weakness is that, when you go from low to high or high to low, right, the flip need you will need two clocks to encode 1. Okay, right. So this is holding 1 0 and holding 1 1. Right. So it's like you instead of 0, right, you encode 0 as 0 1, right, and encode 1 as 1 0. So the efficiency is 50%, right? So it's like the other 50% wasted. But when you encode 0 as 0, 1 and encode 1 as 1, 0, right? There will be no long stream of consecutive 1 or zeros, at most 2. Okay, right? Like this is too high, too low. Okay, that solved the problem, but again, the bandwidth, right? The clock is not better utilized. Okay. Right, so that's for the physical layer, and the physical layer and the data link layer will combine to have a assignment. Okay, for the quiz. Right, so yeah. So next, let's look at the data link layer, or we can also call it the link layer. Okay. So this lecture will include the link layer will include two slides. Okay, so this is the first slide. Okay. So here, the data link layer, we are sending a block of data frames between physical devices, right? As we said, physical devices, we care about bits, okay? And then we have packets, right? Data link, we have packets. And the packets, in the data link layer, we call it frames, okay? We also call it frames when we talk about packets in the data link layer, okay? It's just a bag of bits, right? And also we see that, for example, UDP, right? So called the datagram, for example, the transport. Okay, but in the data link list, frame is the frame is a packet name in the data link layer. Okay, so it's just a packet, but when it's in the data link layer, we call it frame, right? And we send the data frame between physical devices, right? And why is this data link layer is important, right? So we need to regulate the access to the physical media. So the reason is very simple. Think about it. Let's say you are using Wi-Fi, okay? And if both two people are standing together in the air, right? And then this, for example, you have a high signal, the other guy also have a high signal. When you have low signal, the other guy also have high signal, right? So then it's just a garbage information, right? So you cannot have two people talking together, two devices standing together, okay? You need to have the media control, right? So this is called a medium access control, okay? Another thing is that you may have errors, right? When you send stuff, some other device send some waves, right? And flip some bits, right? So how can we detect errors, okay? And a more important problem is really how we delineate frames, right? So keep in mind, the data link, we are sending frames, but frames ultimately are 0, 1 bits, right? Which physically you care about, okay? So how do we know the boundary of each data frame, right? This is the bits for data frame 1, that's the bits for data frame 2. Okay, we need to have a way to delineate the frames, right? We need to know the boundaries, okay? And finally, how can we recover from collisions, right? Collision means two people talk together, right? And then you need to find a mechanism, right? A mechanism to, to back off and maybe restand again, for example, right? So you need to detect the collision, right? Avoid the collision, if possible, totally, right? Sometimes this is possible because you can listen on the media, right? If someone is talking, you can avoid talking, okay? But we will see how these things are designed, okay? Right. Firstly, framing, right? So framing means that we want to group bits into frames, and then send a because frames are the basic unit that router handles, right? So I mean so we need to have those bits grouped into the frames, okay? So physical layer just determines how bits are encoded, right? We see that how 0 is encoded and 1 is encoded, right? Maybe a consecutive 4 bits need to be encoded 5 bits, replaced with 5 bits, and one receiver side need to be decoded back, right? So this is what physical layer care about. It doesn't care about the blocks data, right? We call it the frames, right? So, but we are using called a packet switched networks, right? Which means that the router takes the packets and send packets, right? The packet it receives can be from you, can be from other people, right? So then we need to actually group the bits, okay? So that the router and the link in the call into call can be shared by many people, okay? So each packet actually includes a routing information, right? And this is very important, okay? And in the In the data link layer, we also care about routing information. Okay, for example, you can be in the same wireless router, right? A lot of laptops are connected, right? How do we send stuff around, right? So whether from laptop 1 to laptop 3 or to laptop 2, okay? So we still need a routing information, but this is really your subnetwork, okay? And so the router really route beyond your subnetwork to other people, okay? Maybe physically a long distance, not in the same subnet. Okay. And the data boundaries must be known, right? So the headers can be read, right? So you know that, hey, this is the beginning of a data frame, right? Then we know that we last time we see there's a header concept, right? So for example, for the transport layer protocol, we may look at IP address and port number, right? Okay, right. So for the data link layer, maybe we care about the, like a MAC address, right? Access control concepts, okay? And so there are different ways of framing. It means we cut things into frames, okay? To cut a bit stream into frames. And the first one is called the byte-oriented protocol, right? So basically, the checking is in a unit of bytes, okay? The second is called the bit-oriented protocol, which means the checking is even more fine-grained, right? So you look at the bit one at a time, okay? And there's also clock-based protocols. That means that, we have a clock, right? And the clock, each clock, you may have more than one byte, right? You can have a larger portion of data, but because the clock is perfectly synchronized, okay, so then there will be no issue there, right? Otherwise, if you don't have a clock there, okay, then you need to really look at the byte or bit patterns to delineate different groups, okay? Okay, I see a student asking for leave. It's fine if you have urgency, okay? Yeah, let's continue. Okay, so let's look at the three methods, right, we talked about. The first is byte, the second is a bit, the third is clock, right? If you need a clock, that's more advanced, right? So you need to synchronize the method. So when students ask for data boundaries, we will see shortly, right? So I think we will see it immediately up in the next one or two slides. Okay, so right, so let's begin. Okay, so for example, you have a block of data, right? A group of bits, right? A block of bits, okay? But that belongs to one frame, okay? But it's sending in a while, but you don't have a clock, right? If your standard receiver has a synchronized clock, then that's fine. But you don't have a clock, right? One clock, one frame, for example. Then that's a perfect method, right? But you don't have that, right? How can you handle this problem? Okay. Right here we are talking about byte-oriented method, okay? So then you can add some like a sentinels, right? Which is like saying that, hey, this is starting a frame and this is stopping a frame, right? Again, these bits will be wasted. Okay, these bits will be wasted. Okay, but that's fine. That's delineating, right? So maybe there's another data frame before, and then we see the bits. We know that data frame ends. I should start to receive the next data frame, right? And we read it. This is because you don't need a clock, right? Then you need to have some signaling stuff, right? Like the sentinels. You have a start and end sentinels for each data frame. Okay? So the problem comes here, right? So what if so these start and end sentinels are particular bit patterns, right? What if this bit pattern also happen in the data, right? Then what will happen that I will think, hey, I end here instead of here, right? And these are actually data payload, right? The actual content people care about to the upper levels, right, in the network layer for them. Okay, so how can we handle this? So we will use escapes, right? So this is called because it's in a data link layer, we call it data link escape, right? DLE. Okay, this token, and the start token, end token, DLE token. Okay, so the DLE token, the name you need to memorize it. DLE means data link escape. Okay, because we will test you in the quick. Okay, so we have three special tokens, right? So now if we before the end token, we have a DLE token before. Right? Keep in mind these tokens are all bytes. the data are checked in the unit byte. Okay, we have a DOE byte. Then we know that what is following is actually the content, not the end, the special type. Right? This is called escape. Okay. So then, what if, for example, this is next one. What if DOE is this special pattern is also part of the data, right? Then what we will do is we add a DOE before it, right? The first DOE is saying, hey, the next byte is actually the data, not some special token. Okay, and then this will be interrupt data. Similarly, for the end, we are also doing this, right? If you have two DOE as a data, then you need 4 DOE, right, as a token. Okay. I see a chat. Oh yeah, so DOE token will be added by your network device. Okay, I see a student asked, right? So the actual data is really the red one. Okay, so maybe this data, this data, this data, right? But when you encode and want to put it on the while, right, you will find, hey, this is really a special token. I will add a DOE before, okay, to say, hey, the next byte is the data, okay? And then I find, hey, this is also a special token. Then I'll add a DOE, right? And when I see this special token, but there's no DOE before it, I know the frame ends. Okay, so that's logic. This is like the escape in your program language, like strings. Okay, so here, like in your C string, you will use a dash, then you have the double quotation, double quotes, right? So it's saying that, hey, this quotes are not a strings quote. Okay, it's a content quote, right? It's part of the string, right? But now you use dash to mean what the next character is, a special token, right? Then what if you also have dash as a content, right? So then you add another dash. Okay. If you have 2 dash as a content, then you add a 4 dash, right? So basically, if your string is something like this, right? Then when you encode, right, you need to say dash dash and dash dash, right? This is say, hey, the next character is the content, the next character content, okay? Right. So this is how you encode stuff. So this is the same in the byte-oriented approach. Okay. Let me see the chart. DOE is not manually inserted. Okay, I see a student asking me the question. It's automatically inserted. Okay, it's automatically inserted. Again, I think maybe the student didn't get my what we want to say originally. So we need some special bytes, right? 8 bits, right? Special patterns, byte patterns. Okay, bit patterns of a byte. Okay, to mean start end. Maybe this is 101010. This is 0100. But what if the content is there, right? If you don't have the DOE, you will think this is the end. Okay, now you have a DOE, you know this is the content. Well, if you read here, this byte starting without a DOE, this in special token is truly a special token. Okay, well, this special token is the data. Okay. Do I answer your question? I think, yeah, okay, thank you. And this kind of protocol is used by the point-to-point protocol in the modem and DSL and cellular, right? So this is kind of like you have a one-one, right? We talk about the cable connection using TV, that's shared, right? So if you only have a point-to-point connection, right? You don't have multiple people connect to the same media, right? You have one end and the other end serving you, right? So this is called a PPP, right? Point-to-point protocol. Okay, for those kind of devices, they are using this kind of approach. Okay. Here, here another thing is that we need also byte counting, right? So if you don't want a end tag, right? So you can also add a byte count. Okay. The sender can insert the length of the data in bytes at the beginning of each frame. Okay. If that's the case, you know that you don't need the DLE in the middle, right? Because if you say, hey, this starts, okay, and now the next one is a size, right? The size can do not even need to be 4 bytes, right? Maybe 2 bytes enough, depending on how large your frame is allowed by the device, okay? And then even 1 byte sometimes, okay? So this encodes the length of the data frame, okay? And then you just read so many bytes and it ends, okay? So this saves the DLE because if you have a lot of special tokens, right, and you add a special tokens, the worst case utilization rate is 50%, because for each byte, maybe you need a DLE before, right? And if you just put a size in the beginning, you can save that effort, okay? But of course, if you don't have any special token in the middle, right, then this one is wasted, right? Because you know that ends, right? So so that's trade-offs. So the sender can insert a length of how many bytes you have at the beginning of the frame, right? Then the receiver just get the length first and then read the that many bytes. Right? Then you don't need DL. So this is called byte counting, right? So the next method is called bit-oriented, right? So the device will check 1 bit at a time, okay, instead of byte, right? The benefit is that you don't need an entire byte boundaries, right? So for example, each byte is 8 bits, right? Then you need 8 bits or 16 bits, because each time you check a byte, right? Even a special token is 8 bits. But in terms of the number of bits, it's a little bit wasting, right? So bit-oriented method, sometimes you can save some bits, okay? So here we are adding sentinels to the start end of the data frame, okay? Both sentinels are the same. Okay, so basically we don't need 2 special tokens. Okay, then we have only half the probability that we will have conflict, right? So so here this is a special token 0 1 1 1, but it's still a byte. Okay, in this case 0 1 1 1 1 1 1 0. Okay, both are inserted there, right? So this one means the start, the other means the end. Okay, but we will have the same problem, right? So what if we will see the same 8 bits, right, in the middle of the data, right? Then I don't know whether it's the end of the data payload, right? Then we are also in trouble, okay? So this string is an example of the high-level data link protocol, HDLC protocol, okay? And there's different bit-oriented protocols may have different string bits, okay? All right, so then how do we avoid this thing to happen in the middle, right? So one way is we can use another escape token, right? Then we need 2 bytes to encode 1 byte, for example, right? Like before. But we might think this is quite wasteful, okay? Because in the worst case, every byte needs another byte before it to say, hey, this is data, right? And think about just the special tokens itself repeated many, many times, okay? So this is 50% utilization rate, right? Can we improve the worst case utilization rate? Right, the bit-oriented method will do so. Right, let's see how this is achieved. So we see that we can have 1 1 1 1 1 1 6 ones, right? So we will require not data in here can have a consecutive 6 ones, okay? Right. So to achieve that, our device the sender can insert a 0 after every 5 ones, okay? Whenever I already see 5 ones, I will automatically insert a 0. And this will not cause problem because on the receiver side, if you see consecutive 5 ones, well, you will remove the zeros after it because you know that there must be a 0 there, right? If you see a 1, then it means the end, okay? Right? Otherwise, you will always see a 0 and you will remove it because you know that it's data payload, every 5 1 bits you will have 0, okay? But if you only have 3 bits or 4 bits, right, of ones followed by 0, you know that these are all data, okay? So that means, you don't always need to insert a 0. Only when you see 5 ones, you know that the next should be a 0, which is wasted, but just to avoid conflict with this token, okay? So this is known as bit stuffing. The benefit is you can stuff a bit instead of an escape byte, right? So on the receiver side, the logic is looking like this, right? So if you see 1 1 1 1 1 5 ones, right? If you then see a 0, this 0 must be a stuffing 0, okay? Because you know that if anything in the data frame have 5 bits, the sender will always insert a 0, right? Which is this 0, okay? Right. So you will just remove that 0, okay? Right. Assume this is not in the bit stream, okay? I see another question. Yeah, the sentinels are just a start end, okay? So, just like before, but this time we use the same one, okay? The same one with 6 bit, 1 bit, okay? And now, this is when you see 5 ones and then follow by 0, right? So the other case, else case, right? You see a 1, okay? You see a 1, then you need to look at one more bit, okay? Right, look at the next bit, right? If the next bit is 0, you are pretty sure this is the end of the frame. So this data frame end. Okay. That could also be happening that you have 1, 1, 1, 1, 1, 1, 1, and here it is also 1. That means you have 7 ones, right? The only possible case this happens is because some bit is flipped. Okay, right? Like originally there's a 0 here, but you flip into 1, right? And all this 0 is flipped, right? So you have 2 blocks 1s which are small, but because they are 0 flipped to 1, you have a long segment, more than 6. Okay, because in our encoding method, you will never see more than 6, right? In the data payload, at most 5 consecutive ones, and on the setting nodes, at most 6, right? So if you ever see more than 6, then that frame is corrupted. You drop it, and maybe the protocol will ask for retransmission. Okay. Okay. So what's a bandwidth width in this case, right? So we can show that this is a 20% as a width, right? So reason is very simple, right? So because you think about it, if you have so many, you have five bits, right? So 5 ones, then you will insert a wasted bit, right? So this is like every 6 bit, you have 1 bit wasted, okay? Right, so it's actually less than 20%, okay? So, and of course, you are not counting those bits which are not the payload actually, right? It's just a stuffing, it's just the settings, okay? Right. These are always needed because you want to define the boundaries, right? So if you add back those, and every 6 bits you have 5 that are useful, but you also with something, it's around 20%. Okay. But again, so let me see. Yeah, so this is a more this is more, in the worst case, this is more friendly than previous method. Right? The previous method you have 50% in the worst case, because whenever you want to differentiate from the setting node, you need a whole byte before the current byte. Okay, now you just need add a 0. Okay, this is more efficient, right? Any questions? And we are talking about at worst, because if your data never, let's say in the data stream, you never have 5 consecutive ones, at most 4 consecutive ones, then you never need to insert a 0, right? Because if you have 4 ones and then followed by 0, this 0 is data. Okay, only when you hit the sensitive 5 ones, right? Then you need to add a 0. Okay, so a lot of times you don't even need to add a 0. Okay. So the next one is clock-based framing, right? And this is like a SONET protocol, and it's often used in the optical networks, okay? And it's a fully synchronized optical networks. Why we need this? Because sometimes the bandwidth so high, right? So like a cross ocean, right, between different continents, right? So in that cases, we always use light to do the transmission, right? Optical cable, okay? In that case, using the previous method will be not quite efficient, right? So because that one clock, because your bandwidth is so high, we transmit a lot of bits and bytes, okay, right? Then you cannot afford using just 1 bit or one byte at a time to check whether the next thing is worse, okay? Because each clock you send a lot of data, right? So this is really this is called SONET is the full name is synchronous optical network, okay, SONET. Right. This is really for transmission over very fast optical links, right? Because 1 clock is really a lot of bytes. Okay, an example is like the STS. STS is the synchronous transport signal. Okay, the shorthand notation for it. Okay, and this is the version, the version. Okay, this is version 1 is 51 megabit per second, right? But if you look at this version, right, you can see it's already almost a 40 Gbps, right? It's crazy, right? It's almost an infinite band, right? So these are really fast, right? You think about in 1 second, right? So many bits are sent, right? This G means billion, right? Right. This is 40 billion almost, right? At least a 37 billion bits are sent. Okay. So you cannot just check a bit by bit, back, right? So we do need some clocking mechanism and do synchronization, right? And once it's synchronized, then we just need to tell, hey, this is start of a data frame, right? That's all we need to do because there's a clock to synchronize, right? So we need a special start pattern, which is the overhead. Okay, and then we can send the payload. Right. So this protocol, right? So the STS1 protocol, the frame structure, right? This is the frame version. Okay, it's based on the fixed size frames, right? Because the clock is fixed, right? Our frame size also is fixed, right? So it's just send a frame using that many clocks. Okay, right. And the size is actually 9 by 90. Okay, and the first node, there's a small overhead at the beginning, right? So you can see, just one frame sends so many bytes, right? So because it's very fast optical links, so we have to do a synchronization of the clocks. Okay. So the details actually is that our bits are encoded directly using NRZ, right? So NRZ, we know that this is not a very safe method, right? Because we have the NRZ I, right, inverted, right? And we talked about matrix thing, right? So, but those methods sacrifice the bandwidth, right? There's some overhead, right? Just like encoding 4 bits to 5 bits. But you think about such high bandwidth, right? And sending so many traffic across the ocean. If you waste maybe 20%, that's a big deal, right? So we just using this method without any waste, okay? But because we have the synchronous clocks, right? It's clock based, right? So that's fine because we have the clear clocks between these two parties, okay? And so the payload is also XOR. XOR operation means that you can have a special pattern, right? So your original byte is like this, right? So your original bit is like this. We can have another bit pattern, like exclusive OR with them, right? So this bit pattern, if exclusive OR operation, if you do 0, then you will keep the bit, right? If you have 1, you mean you want to flip the bit, okay? Original 1 then becomes 0, becomes 1, 1 becomes 0, okay? And by this kind of flipping change, right? So you can make sure there's no long sequence of 0 and 1s, okay? You can design this bit pattern carefully to achieve that, right? And on the receiver side, because you know the special pattern, you can exclusive OR and get it back again, right? So exclusive OR is the operation that if you have A, x equals A, it's equal to 0, which means that you can cancel this bit, right? But when you send, you make sure after the exclusive OR, there's no long, there's no long sequence of 0 1s because we are still using NRZ and we still want to avoid this, okay? Even though we have a clock. Is this clear? So this basically completes the 3 methods, right? So the first is byte based, another is bit based, and this one is clock based. Okay. So this talks about how we can differentiate the different frames from the bit stream. Right? So this is the first topic in the data link layer. The next one is noise. Right? So how can we deal with noise? Okay. So why we care about this, right? If you send 1, why the other side that bit will become 0, or you send 0, why the other side will become 1, right? So that's quite confusing initially, right? So this is because the physical world is inherently noisy. Okay, you can have interference from electric cables, right? So like there's a transmission tower, and then there's some electric waves, right? And then interfere with the signals. Okay, right? So and that could even be microwave oven, right? So if you are using a laptop and you are also heat some food, right? Then there will be some crosstalk, okay? Because they are in the same frequency, okay? As we can see later, right? So the Wi-Fi, some protocol will use the same bandwidth, okay? The same frequency as the frequency bandwidth as the microwave. Okay? Then you definitely have some bits flipped, okay? And there's also like solar storms, right? So this is a little bit crazy, right? So but if you think about the devices sent to the outer space, right, to the universe, okay? What happened is that these devices need to do some called a Byzantine error, right? So for torrent, okay? Because there's all kinds of electric signals in the outer space, right? In the universe, okay? Like solar storms and other kind of I don't know, maybe dark matters, etc. Dark energy, and I don't know anything that can just interfere with us, right? So because we have the atmosphere, right? Outside there's no protection, okay? And then, you know, if you just don't do those kind of fault tolerance mechanism and send something into the universe, right? So then the you know, these kind of, you know, the devices can may not work anymore, and maybe you know, those spaceships will crash. Okay, so people need to do the Byzantine error, which probably we need some redundancy, right? We compute it 3 times using 3 different devices in parallel, and if we find something different, we will recompute. Okay, because you can never know how this bit is flipped, but it's very unlikely, you know, because the signal has a direction, right? All these 3 devices in the row are flipped, right? Okay, so this is another source of noise. Okay, so how do we detect this bit errors in transmission, right? And whether we can even recover from errors, right? Of course, a naive way of recover is just a retransmit, right? But can we sometimes, we can see, hey, that bit is flipped, okay? That's the ideal case, right? So if you can do something like, I know exactly in the frame, so the 56 bit is flipped, then I flip it back, right? Then I don't even need a retransmission, right? So this is even better, okay? So let's look at some approaches. Okay, so the naive error detection method is just like the Byzantine error method. Okay, Byzantine fault tolerance method, which I think is used a lot when you, like, for example, you design some devices for NASA. Okay, right? Because you know, outer space there are so many signals, right? So you can send 2 copies of frame, right? So it's just a redundancy, right? You send frame 1 and then send frame 2 they are the same data, but twice to the receiver. Okay, then the receiver will also receive twice, and then they will compare these bit streams of these 2 data frames and see whether they are exactly the same. If there's any bit that does not match, I will know that there's an error on the receiver side. I probably can ask for a retransmission, right? And then I will not take this wrong data and then move to the processor. Okay. But actually, unless you want it to be Byzantine error fault tolerant, right? Otherwise, this is really a bad idea, okay? Because there's a extremely high overhead, right? So whenever you send something, like you send a 10 GB movie to your friend, you need to send 20 GB, right? So that's, I think this is pretty intuitive. And the protection against errors, you know, is also not good, because if you think about it, you send the data twice, right? So, and if assume your data frame is actually quite long, right? So, and if there's a solar storm, right? So your bit in a frame can easily be flipped, right? And this time you flip this bit, that time you flip that bit, right? And you even if they are not the same bit, you detect the error, right? But you know, the protection is poor because I can retransmit it again, there's some error, and I transmit again some error, right? So because, you know, you cannot recover them automatically. Okay, I see a question there. Oh, there's a student asking about overhead, right? So overhead means something like a. So overhead means if you want to just send a 10 GB movie, right? If you send this, you need to send 2 movies and then compare their binary stream, whether they're same. So this is the actual data you want to send. Overhead means additional data, right? Not the data you want other people to send. This is a useful data. This is just data to make sure this is correct, right? But this is overhead. This is not used. Okay. When you look at what is overhead, it means whether you have additional data bits that is sent, because when you send a bit, you use some bandwidth in the metal device, right, in the link. But if it's actually finally not useful, right, then it's an overhead. Okay. Similarly, in our previous examples, if you use, for example, the start and end token, right, setting nodes, these are overhead, okay, because you don't need them. You only need this data, right? Okay. And if in the data you insert some zeros, which actually will be dropped later just for the robustness of transmission, right? And these are also an overhead. Okay, this is the overhead is you know, a terminology, meaning that it's actually not the content you want to receive, right? You just want to add those things to be more robust, okay? Whether to errors or to the, you know, to the delineation, okay? And when you talk about the actual data you want, these are called the payload. And so the payload, okay, the actual load you want, right? You paid, right? These you don't want to pay, right? Okay. Any questions? Do I answer your question on the terminology? Okay, let's continue then. Yeah, so you can see if you send twice, then it's 50% of the bandwidth overhead, right? So it's not good. Then can we do better? Again, if you want to Byzantine for torrents, you have to do this, okay? Byzantine for torrents, okay? And one method, we will see a few methods. Okay, the first method is, oh, there's a question on the recording time, right? So yeah, I will upload maybe in a couple of hours, you will be able to watch it, okay? And for the parity bit method, right? So it's not a redundant method, okay? We will see, okay? So parity bit method is called, we will add an extra bit to keep the number of ones even. What does that mean, okay? So here we will have 7 bits of ASCII characters, which are actual characters we want to send. But we will also have an additional bit, right? This becomes a 1 byte. But the heading bit, okay, is really just a redundant. It's an overhead to make sure our byte is correct, okay? So here's an example. We will have, so again, you can see here, this is ASCII character, which means, you know, this is 7 bit, okay, 4 plus 3. Okay? But we have a byte unit, right? So this bit is added so that we only have a, you know, the number of ones, right? So the number of ones is odd, or the number of zeros is even, okay? Right, so for example, if we have, here you can see the whole byte, we have 5 ones, okay? Right, and this, let me see how to see this. I think there may be some errors here. Yeah, so here's, we want to make the number of ones even, right? So let me see whether it's even. This is 1, 2, 3, 4, 5. It's 4, 5. Right, so this should be 1. Sorry. Okay, I think this is a typo. Okay, and this is let me see. I think maybe the animation is a little bit confusing. Okay, I think we should look in this way. Yeah. So this is 1, and this is 1. Okay, and this is 1. Okay, and this, for example, this is 1. Right. So because the distance to the trailing bit is a little bit closer to the. Okay. So here, if you look at here, we have 3 ones, right? But we want the ones to be even. So I add another one, which becomes 4 ones. Okay, and there we have 4 ones already. We add a 0 because, you know, already 4 ones. Okay, this one is again 5 ones. I want to make it a 6 even. Right? All the number is not okay, right? And here we have, for example, 3 and 4. Okay, this is also 3 and 4. Okay? So depending on how many ones, right? If that's all the number of ones, I'll add another one to make it even. Okay, in the byte. Otherwise, I just use it. Okay? So then we can detect one bit of error, right? So for example, if this one somehow flipped to 1, then we already have 6 ones. But I have another one, then it becomes 7, which is the odd number. But I know that if it's correct, the number 1 should be even. Okay, so if you have a 1-bit error, we can always detect. Okay, but this is not reliable to bursting errors. Let's say if we have 2 bits flipped, right? Then you cannot detect, right? This becomes 1, but this becomes 0. Then the sum is the same. That's still the number 1. It's just one in these 2 bits. Okay. So we will need a better method like the 2-dimensional parity method, but we will discuss that next Monday. Okay, let's take a quick attendance. Let's see. I see a question. If you catch an error in these streams, do you just flag that byte and send? So depending on whether you can detect, okay, so there's an error detection and error correction, okay? detection means I know that that thing I cannot use, because if I use and do the processing again, maybe the spacecraft will crash, right? And I will ask for retransmission on hold, right? So I don't do the action. Maybe it's a wrong action, okay? But if your parity scheme, you can see later we can actually correct some bit if it's a 1-bit error, okay? Then you can just correct and move forward, right? All right, let's just sample 3 people, okay? Diego, are you here? Diego,
here.
okay, thank you. Amanda, are you here?
Here.
Thank you.
I'm here.
Okay. Luke, are you here? Luke Norris? Okay, so let me go to the others.
Yeah, I'm here. Sorry.
Oh, yeah, sure. Yeah, so that's all for 334. Okay, I have 534, and you are free to leave if you have no question. Okay, let me also sample 3. Okay, Aisha, are you here? Aisha?
Here.
Okay, thank you. Let me sample the next one. Arohan, are you here?
Yes, sir, I'm here.
Okay, let's go to the last one. Sweta, are you here? Sweta Turaka, if I pronounce correctly. Are you here? No? Okay, so that's the end of this class, and I will see you next Monday. And it's the lab. Okay, so don't forget to go to the lab. For quiz 2, there's a question. Okay, so I'm answering the question. For quiz 2, you are supposed to look at let me refer the slide. Let me see. Yeah, we have gone through. Let me open that. Okay. We have gone through. Just one more. I think my computer got stuck. Okay, maybe I just play it. We have gone through this slide. Okay, so then we have a few math questions, math calculations, right? So especially this kind of formulas. Okay, and as long as you understand this, like math calculations, then you should be able to answer the quiz 2. Okay. Do I answer your question? I think it's Guavia, right? Guavia Pabla.
Yes, I got it.
Yeah, just want to make sure. Yeah, the student asked about Monday. Yeah, I just say the next class is on Monday, right? So I will continue on Monday, okay? And the next one will be lab, of course, okay? And any other questions? Yeah, if you have no more questions, I will see you on Monday. I will upload the video, and once it's ready, I will just send the link in Canvas, okay? And announce. Okay, thank you, and have a nice weekend. Bye.